Good morning guys and welcome back to Dynamics course. In this video lecture we're going to start a new chapter, chapter 13 in the textbook, and this chapter is about kinetics of a particle. And as you know from the introduction of this course, there is a difference between kinetics and kinematics. Kinematics, guys, deal with the variables that are acceleration, velocity, and position, while kinetics deal with the causes behind these variables, and these are mainly the forces. So if I have a body or a particle subjected to forces, these forces will change the velocity of this body, or will cause a change in position, or will cause what is called acceleration. So it will cause what is called the inertia force, which is related to acceleration. All right, so we're gonna discover what are the causes behind kinematics, or in other words, we're gonna discover the kinetics of a particle. We're gonna discover the forces exerted on this particle. So what are the objectives of this chapter? In fact, they are to write the equation of motion for an accelerating body and to draw the free body diagram. And don't forget, guys, what is a free body diagram? A free body diagram is a diagram showing the external forces exerted on this body. Because in fact, I'm not interested about the internal force, since their sum is equal to 0. Whenever I take a body, then this body is exerted or is subjected to external forces. These external forces will cause the acceleration or the change in velocity. And then I'm going to apply Newton's second law. Remember what is Newton's second law? It's that sum of forces is equal to ma, where m is the mass and a is the acceleration, to determine the forces and acceleration. I can have an unknown in the forces, I can have an unknown in the kinematics variable. So I'm gonna find it by, in fact, solving the equation of motion, or solving for kinematics as well as solving for kinematics. All right. So in fact, guys, kinetics is used to determine some forces. Like in this example, I'm going to determine the tension force in the cable required to lift this elevator at a given acceleration. So what is the tension force here in this cable that allow me to lift this elevator for an indicated acceleration, a target acceleration? How can I find this tension? Of course, by applying the kinetics law, or by applying Newton's second law. So let's make a review about Newton's law of motion. The first law states that if I have a particle that is at rest or moving in a straight line at a constant velocity, it will remain at rest, right? Because in fact, the resultant force acting on this particle will be 0. The second law states that if the resultant force of the particle is not 0, then this resultant force will be equal to an inertia force, which is m times a, the mass times acceleration, and this will cause an acceleration in the same direction of the resultant force. So if the resultant force is, let's say, horizontal to the right, then this body will move with an acceleration to the right, all right? So this acceleration has a magnitude proportional to the resultant force. We know because in fact it will be equal to this sum of forces over m, or to the resultant force over the mass of this body. Now the third law is about action and reaction, and we know, guys, that mutual forces of action and reaction between two particles should be equal, opposite, and collinear. So let's focus on the second law of Newton that states that the resultant force, or the sum of forces, is equal to ma. For example, if I have this free body diagram of this body here, and I know that I have two forces, F1 and F2, and that the resultant force will be in this direction. Let's say, for example, it's horizontal to the left, then of course, guys, this particle will move with an acceleration to the left, and this will be equal to this resultant force will be equal to ma. And since m is a scalar quantity, then a in vector, or a in vector form, will be in the same direction and collinear to f resultant, all right? So f resultant here is horizontal to the left, then a is a vector that is horizontal also to the left. Now, guys, if I wanna talk about some particular forces or some common forces that we all face in kinetics, I'm going to start by the weight. And in fact, the weight is derived from the mutual attractive gravitational force stated by Newton. So, you know, of course, guys, that the weight is if an external force exerted on the body and it's equal to the mass times the gravity. And guys, I want you to make sure that if you are in SI units, the gravity will be 9.81 meters per second squared, while if you are in US units, this gravity will be 32.4 feet per second squared. Now, the second particular force or common force that we can face is the normal reaction. And you know, guys, that when a body touches another body, there is a reaction force between these two bodies, and this force should be normal. It should be perpendicular to the surface of contact. So if the surface of contact is horizontal, then the normal force will be, of course, vertical. However, if it is oblique, this normal force will be oblique, perpendicular to this separate or to the surface of contact. Now, if it is curvilinear, then this normal force will have the normal direction. All right. Now, another particular force is the tension. All right. So the tension is in fact created inside a rope. So, for example, here this tension is inside this rope that holds this body. Now, here I have two tensions, T1, T2. In fact, I have three tensions, T3, T2, and T1. And also in pulleys, I also have tensions, right? And remember, guys, in chapter 12, we talked about the pulleys and the dependent motion, and we focused on acceleration, velocity, and position. Now, in this chapter, we're gonna discover the forces causing these variables, or the forces causing this dependent motion, and it's all about the tension and the weight. Alright, so we're gonna discover how to find these tension inside these ropes, and we're gonna also make a small review because I'm gonna use, of course, the equation of motion from dependent motion of chapter 12 and put them here in order to find, for example, one unknown and these forces like the tension. Alright. I can also have a friction force, and remember, guys, that the friction force is always opposite to the motion. So if this is like, for example, this is the motion, I have like a pushing force, and this is the motion, and I have a contact with a certain support. Of course, I also have here a normal force. Then the friction, guys, will be opposite to the motion, all right? So if the motion is to the right, this friction will be to the left. So if a moving particle contacts a rough surface, it may be necessary to use the frictional equation, which relates the kinetic frictional force Fk and normal reaction N acting on the surface of contact. And don't forget, guys, that this Fk will be equal to mu k times N, where mu k is the coefficient of kinetic friction, all right? Fk always is in the opposite direction of the motion of the particle relative to the contact surface. Now, I can also face an elastic force, and this elastic force is created because of the presence of the spring. And don't forget, guys, that always this force, guys, is towards the equilibrium. So it always acts to restore the spring towards equilibrium. For example, guys, if I have this body here and I'm stretching the spring will have, stretching the spring to the right, the spring will always have a force to the left because it always want to restore the spring towards equilibrium, and the equilibrium here is to the left. Now, if I do the compression, this means that, of course, the elastic force will be to the right because the equilibrium was to the right, all right? So I'm doing a compression, then the elastic force will be to the right. I'm doing a tension, then the elastic force will be to the left. And what is the magnitude of the spring force? It's always equal to K times X. And what is K? K is the stiffness. It's the constant for the spring. It has the unit of Newton per meter. But don't forget, guys, that this X is L minus L0. It's the elongation. It's L minus L0. And remember from statics, guys, what is L? L is the current length. It is the current length at this time, while L0 is the initial length. It's not the initial length at state 1 or at the previous state. It's the initial length when there is no forces exerted on this spring or on this body, which means it is the initial length of the spring at equilibrium. Alright? So L is the current length minus L0, which is the initial length. Which means, guys, if I am at state 2, L0 will not be the length of the spring at state 1. No, it's not the previous length. It is the length at state 0 when there is no forces exerted on the spring, while L is the current length at this state. So don't forget, guys, X is equal to L current minus L0 when there is no forces.